Good evening. On behalf of the Goodman Cancer Institute, it is my pleasure to welcome you to the first of this year's public lectures. I'm Joe Schwartz. I direct McGill University's Office for Science and Society, where we have a mandate to separate sense from nonsense, fact from fiction. And as you can imagine these days, that is very challenging, especially in the case of the most dreaded disease out there, which is cancer. There's a tremendous amount of misinformation when you just cruise the internet. Frightening, but it is also possible to tune in to solid information. And that is what we focus on here at the Goodman Cancer Research Institute. To make sure that you get reliable information about cancer and about the research that is going on, and don't get distracted by a lot of the nonsense that you'll find on the internet, we have asked Dr. Michelle Tremblay and Dr. Kellyanne Pike to discuss their research with you. Dr. Tremblay works here at the Goodman Cancer Research Institute, and Dr. Pike trained under Dr. Tremblay. But now she works in private industry. And that is a very interesting connection because it shows how information gets transmitted first to industry and down to the average person. The impact of the Institute is clearly seen through the translation of this information. To get things rolling here tonight, we will ask Dr. Morag Park, the director of the Institute, to open proceedings.
Hello, and welcome to the first public lecture series of our calendar year. This is the first public lecture since becoming an institute. And over the course of the year, our goal is to help you understand what that means. The Institute, as you will see, is a call to action for change in how we do cancer research. Our ultimate goal is to push the boundaries of cancer research to come closer to a cure for hard-to-treat cancers. Our talk this evening will highlight how the Goodman Cancer Institute mentors the next generation of leaders in academia and industry. I'd like to introduce our co-chairs, Jonathan Durocher from Banque Nationale Financial and Paul Sislian from Bombardier Transport. But first, let's hear from Stefan Larsson, the chair of the Public Lecture Series Committee.
As a biotech entrepreneur and investor, I've been able to witness firsthand the power of collaboration between academic research and private sector biotechnology companies. And here at the Goodman Cancer Institute, we certainly believe that fostering collaboration between academic scientists and private biotech companies is a very important part of being able to bring innovative therapies and curative therapies to the hands of patients and the physicians that are treating them. And those collaborations can take many forms. It can be in the form of training the scientists here in the academic labs that then go on to work in industry and develop these drugs, or maybe even found companies themselves. It can take the form of active scientific collaborations between private sector companies and the academic groups here. It can be clinical collaborations to run the critical trials that are needed to prove the efficacy and safety of these drugs in patients. Or most excitingly, it can be entrepreneurial scientists who go on to start brand new companies together with venture capitalists and others in the ecosystem.
Hello and welcome. My name is Paul Sislian. I'm the Executive Vice President of Operations at Bombardier. The GCI is a world-renowned research institute based right here in Montreal. It focuses its research on difficult-to-treat cancers and collaborates with the best minds to achieve the goal of improving the outcomes for cancer patients and their families. This is the work that has the potential of impacting millions of families. All of us are watching, and we're very proud to be part of it.
In the current environment, it's important to buy local, bank local, and encourage local industries and research. The GCI's local expertise falls right into that category, and we're both proud to be associated with their groundbreaking research.
So, without any further ado, I'd like to introduce Mr. Laurent Amram, President of CDL Labs in Elna, who is sponsoring tonight's public lecture series. Laurent is a Canadian businessperson and philanthropist, and the founder and president of CDL Laboratories, a leading diagnostics laboratory and business partner of Roche Diagnostic. In 2016, Laurent founded Elna Medical, a network of medical services facilities located right here across Canada. Today, Laurent is focused on transforming the Canadian healthcare landscape by delivering quick access to the highest quality of patient-centered care with the emphasis on healthcare technology. He serves on the boards of several charitable organizations and lends his support to causes including health, education, and at-risk youth.
Chers amis, bonsoir. Merci, Jim et John. Nous sommes ravis de contribuer à une cause aussi importante. CDL Laboratories and ELNA Medical are firmly committed to delivering the very best in quality healthcare. That is why we are honored to join you in support of this evening's public lecture series. We believe in the power and promise of comprehensive care that leverages the most advanced technologies to create the best outcomes for every patient. Comme tant d'autres, nous apprécions énormément le travail innovant et avant-gardiste réalisé par l'Institut du cancer Goodman. Your mission is as noble as it is crucial in saving countless lives. United by common values of excellence, ethics, and integrity, we are also committed to innovation as a means to creating meaningful impact for all patients. On behalf of CDL Laboratories and ELNA Medical, I wish you a pleasant evening. Bonne soirée à tous. Now back to you, Dr. Joe.
One of the critical areas of research here at the Goodman Cancer Institute is drug discovery, because after all, that is the key to battling cancer. And it's very important for information to cascade down through the ranks. Dr. Kellyanne Pike trained here under Dr. Trombley, but now she works in private industry. And you can see how the information is being translated from fundamental research eventually to the bedside. And that is the real impact of the Goodman Cancer Institute. I'm sure you will hear all about it from our researchers, so let's meet them. Dr. Michel Tremblay is a recipient of the Prix de Quebec 2021 and the Wilder Penfield Prize in Biomedical Research. He is the Jean and Jean-Louis Levesque Chair in Cancer Research, a distinguished James McGill Professor at the Rosalind and Morris Goodman Cancer Institute. He's also director of the McGill Regenerative Medicine Network in the Department of Biochemistry. Dr. Kellyanne Pike is the head of Translational Sciences and Scientific Affairs at Ventus Therapeutics. She's also an adjunct professor in the Department of Microbiology and Immunology at McGill University. Welcome, Michel and Kellyanne.
Thank you, Joe. Thank you very much. Kelly, please join me.
Hi, Michel.
Hello, Kelly. So, good evening, everyone. And it's a pleasure to be here and describe to you activities of the Goodman Cancer Institute. The first one is mentorship. We train many young scientists to become researchers, both in academia and the private sector. The second thing we do is to bring our discovery in the basic science to clinical applications.
I'm one such trainee. I did my PhD and my early postdoctoral work at the University of Toronto, and then had the opportunity to join Michel's lab at the Goodman Cancer Center. And during my time at the center, yes, I became a better scientist, expanded my knowledge, but it was also the first time that my mentor really pushed me to think about how my basic science was going to impact patient health. And so what we'll do today is give you a bit of the history around the science that we did together, as well as tell you about how we're thinking of translating that to the clinic, and really hopefully relate to you how important mentorship is and how Michel's mentorship has really allowed me to develop my career in science and in drug discovery.
We will talk about cancer research tonight, but our story starts with a chicken. Not any chicken, this one. This one was discovered by Peyton Rous. He was a scientist, a clinician scientist working on viruses many years ago at the Rockefeller Institute. What you see in this chicken is a tumor, and Peyton Rous found that if you were taking part of the tumor and then transferring that to another chicken, which was healthy, you could bring this tumor to the second chicken. So the tumor was transferable. So from the discovery of Peyton Rous of the tumor in these chickens, it took him several years to just identify that what was transferred from one chicken to the other, the next was a virus. So it was a virus disease that was causing tumor. And it took at least another 30 years to find an assay to calculate the number of virus and how it shows in cells. And this is what you see on the figure, where you have cells put in culture and then cells which are transformed by the virus and they grow as a tumor, if you want, on the plate. And then, of course, the technology has evolved during the 20th century to the point that we were able to map the virus, to know what the genes are in this virus. And this single protein that caused cancer, this was named a kinase.
That's right, Michel. There are two players in our story, two characters. There are the kinases and the phosphatases. And what I'd like to do in the next few minutes is really explain how these two players contribute to cancer. So if we think of this in terms of at the molecular level, the virus will infect the chicken and the virus will make its way to the cells. Once it's inside the cell, the virus will produce that protein that Michel was referring to, the Src kinase. What the kinase does then is activate other proteins within the cell. It's phosphorylating those proteins. Once those proteins are phosphorylated and activated, they'll cause the cell to grow and divide in an unregulated fashion. And so that makes you think of exactly what cancer is, uncontrolled cell growth. You can also think of this in terms of an electrical switch, where the kinase is turning on the light, turning on activity. So what happens in your cells is that you have many switches and you have many kinases, but they're organized. They're actually placed in succession. So you can think of this as yourself walking into a hallway. And as you're walking down that long hallway, you're turning on one light at a time as you're progressing down the hallway, illuminated by the lights, to reach the room at the end of the corridor. So the kinase is turning on those lights as you're walking down the hallway. In a healthy cell, what happens is that as these switches are turned on, they lead to the central hub of the cell. And it's in the central hub of the cell that decisions are made, whether that cell is going to divide, or if it's going to start moving around the body, if it's supposed to die at that point. But just like in your house, you don't leave your lights on all the time. You do need to turn off the lights in your cell. You need to turn off your proteins. And that's where the phosphatases come in. The phosphatases do the opposite of the kinases. They're turning off the light switch. Unfortunately, in cancer, as we learned from studying Src in chicken cells, in cancer, in humans, the kinases are hyperactivated. They're on all the time. They're keeping the lights on. And as a consequence, your cells are constantly dividing or invading into tissues where they're not supposed to be, or they're not dying when they're supposed to die. So Dr. Tremblay's work has really focused on understanding phosphatases, understanding the proteins that turn off the light or turn off the switch.
My work, in fact, all these 30 years that I was at the Cancer Center, was really to understand what this off switch was. And for that, I want to bring you back to many years when I was also a trainee at the National Institute of Health in Washington. So the first reason I went there was to, in fact, try to model novel animal which has cancer, so we can study cancer better. And at those days, there was the time where people were designing techniques to manipulate embryo and then be able to bring mutations in the embryo that will then reflect on the disease that you're following up. This is what I did at the NIH. So we just use mice and embryo and various techniques to create animals without many different genes. So one by one, and when you create these animals, you can see the phenotype, the function of those genes, because they have disease we did not expect it. And I'll give you two examples that we have. The first one was work that we've done. So the work that we've done in neuroscience. So one phosphatase that was identified, there's 107 of them. So you can see there's a lot of work, but we study about a dozen of those. And one of them was involved in the neuroscience, in the growth of, well, we did not know, but they were expressed in the brain. When we knocked it out, in fact, the axon grew much rapidly and much longer. So we were able to show that if you take out this phosphatase, you could improve the length of axon. And in fact, what you see in this model, there's a green dye that we inject in the neuron. And this green dye shows you that if you have an injury, like broken your spinal cord, if you've dive in the pool or other injuries, the neurons are broken. And sometimes if it's a nervous central system, you cannot repair. And so you see the dye on the bottom side of that are not moving forward than the line. However, if you take out this phosphatase, what you see on the top is that the dye goes in, the neuron extends through the injury. So here we go, we had a nice system to study one particular phosphatase that increased the repair of neuron. The other example is an example that I have here where you see these 4 mice. One is obese, and 2 of them are obese, in fact. And this is because these mice have a genetic disease that make them eat all the time. This was identified in the past. And so these mice were like, and we were trying to see what kind of phosphatase could perhaps repair this or help the mice to become a normal weight. So we knock it out the same way in the embryo, and we found mice that were almost normal weight, although they had the mutations to eat much, much more.
So when I joined Michel's lab, he had clearly shown that when you remove certain phosphatases, you have a hyperactivation and an increased number of certain immune cells. But what was even more interesting was his discovery that when you remove just half the amount of this particular protein, you had half the amount of inflammation, suggesting you have almost a dose response. And so this led to a lot of brainstorming, a lot of discussions within the lab about what does this mean about biology and what does this mean about our therapeutic strategy. And so many experiments by myself as well as other researchers and immunologists within the lab led us to really understand that it's actually not an off switch. Phosphatases aren't just turning off the light, but they actually act as a dimmer. So in very much the same way that you can set your dimmer so that you have the ideal light in your room, we can tailor the amount of phosphatase activity in our immune cells to tailor them to our therapeutic needs, to make them better killers, for example, of tumor cells. So thinking about tumors and cancer and how we can use immune cells therapeutically, we know immune cells can kill our tumor cells. However, tumors are sneaky, right? So they know how to disguise themselves so that immune cells don't recognize them. They also know how to sort of suppress the activity of the immune cells. So what we hypothesized and began to look into is whether or not we could dim the phosphatase activity in certain immune cell types, and then that would increase their ability to recognize tumors. That would increase their ability to kill tumors. And so this was really a hypothesis that we did the mouse work to try and build up some evidence to support this hypothesis. And now we're at the stage where we're trying to move this into the clinic. And Michel, I think you're best suited to sort of explain the clinical strategy that we're moving forward with.
Thank you very much, Kelly. So now that we knew we could maybe modulate, so we needed a drug, so there were few drugs available now that we're developing against this enzyme. And what we've done, and we've looked at this idea, is that if we can reactivate cells for their property of killing tumors, we can maybe make a therapeutics. And so the example that I have on this schematic is that this is the plan that we have now for clinical trials, and it's moving along. We have done quite a lot on this. So the idea is just you take from a patient which has a tumor, the blood of this person, and you isolate particular immune cells. Immune cells that are not very good now to kill the tumor. The tumor plays all sorts of tricks on this patient. So we can then differentiate them, make them be a much more interesting immune cells, and then we activate it with a compound and many different, it's a cocktail that we put, but it's outside. So the patient has now his cells or her cells activated to recognize, because we give a bit of the tumor to this cocktail, and the cocktail now is used to, in fact, activate the cells and make them recognize the tumor. Then the last part of this is take those cells, retransfer to the same patient, so it's called autologous, it's their own cells, they don't have a side effect of that. And these cells will then go into the body of this person, and seek the cells that will kill the tumor, activate them, and this is where the therapeutic works. The cells will go and reach the tumors and start killing them one by one by one. This is a process of immunotherapy, and there's many directions for that, much basic science to be done. But what we need is, in fact, to bring this to the clinic we need partners.
You're completely correct, Michel. So even though I'm now in industry and a small biotech, we heavily rely on the basic science that's ongoing at places like the Goodman Cancer Institute. We use those findings and those new discoveries to help us think about new drugs to develop and how best to attack pathways that have been identified as driving cancer.
So this is the story we had to explain to you something we did 30 years ago that is brought now to very close to the clinic. There's many other examples of that at the Goodman Cancer Institute. And it's important to think that all these trainees are also spreading around the world in different institutes, at different also companies, starting them and contributing to development, research, and also novel technology for treatment of cancer. So the impact of everything we told you about and all the work of the people at the Goodman Cancer Institute is incredible in terms of quality of life of people, new development of technology, new partnership, and bringing all this broad research towards the clinic. So I think it makes a difference, and we thank you for being there tonight.
Thank you both very much. It's time now to move on to the question and answer part of the evening. So you can pose your question to the researchers and find out what their work is all about and the impact that it has.
You sound, Joe.
And now, of course, it is time for our Q&A, question and answer period. And all of our viewers are, of course, welcome to pose their questions. But let's get started. There's a very large elephant in the room that cannot be ignored, and that, of course, is the pandemic. So I think that we have to start with a question about that, and perhaps we'll start with Dr. Tremblay and ask how the pandemic has influenced your work, how it has influenced your research, whether or not there's anything that you are doing in connection with COVID, what we can look forward to.
Well, thank you, Joe. Good evening, everyone. The pandemic was affecting us in many different ways. Of course, like everybody else in the society, we had to reduce our hours. The laboratory continue working, but people were distant, so we had to spread our hours from 5:30 in the morning to past midnight. So this was certainly what happened. But in terms of COVID directly, I'm also another hat on the regenerative medicine at McGill, and I wrote a small piece with Ines Colmaga, clinicians at MUHC, on the use of stem cells for treating fibrotic lungs. So we did a few things, but not more than that. So that was my contribution, if you want, to the pandemic.
And Kelly, how has it affected you?
Yeah, so I work at Ventus Therapeutics, as was mentioned, which is a small biotech in the Saint Laurent hub here in Montreal. And so we were lucky in terms of we were able to reorganize our workspace to allow us to continue to work, but of course, very much spread out. And many of us worked from home, those who weren't working at the bench in the labs. But I think what it did teach us was how to be more flexible and how to work in such a way that allowed people to work from home and come in on more flexible hours. And so actually it's changed in many ways the way we work on a day-to-day basis. We ourselves as a company haven't refocused our research towards COVID. It didn't make sense for us at the time to be able to pivot and reposition and redirect our research and see a line of sight of being able to impact patient health in a timely fashion. So we didn't think we would be able to do that. So we've continued in focusing on our research on what we were working on prior to COVID.
You went from Dr. Tremblay's lab to private industry. Mm-hmm. And that's quite a transition for a scientist. How did you find that? How did it work out?
Yeah, it's definitely a difficult transition. It does take a change in mindset, especially for me. Like as I mentioned, I grew up, if you will, academically in a very basic science focused training. You know, I still am at heart a basic scientist. I love thinking and debating and discussing and brainstorming ideas to understand really the nitty gritty details about how cells work and how those things go wrong in disease. So I had to readjust coming into industry. I had to focus my thinking to address one question and figure out what experiment I was going to do to address that question in a timely fashion. But in the end, I think it's made me a better scientist because I'm much more focused now, and I'm much more focused on helping patients. So it's in a weird way, it's deepened my thinking because I'm really thinking, what is the critical experiment to address my question to then be able to impact patient health?
Dr. Tromba, you mentioned stem cells before,
Yes.
and that, of course, is a term that is appearing with increasing frequency in popular literature, in newspapers, magazines. Many people, of course, don't really have a sound understanding what stem cells are, but unfortunately, there is a lot of misinformation about stem cells as well. There are some promoters of stem cell research who are putting the cart before the horse and are offering treatments which they claim are stem cell therapies, which actually are not. So what is your view on that?
I think it's a great question, Joe. In Canada, this has not been a real issue because what you're mentioning has been in the U.S. a real calamity. There's a lot of people that are selling, for example, fat cells as a way to treat. There's a lot of stem cells, different types of stem cells, though it's not embryonic stem cells, but people have used those and all these. There's hundreds and hundreds of clinics open on the corner of street trying to inject you with different cells that will cure everything. The worst case scenario was people that had lymphoma. And there was a case where a patient, and that really started the FDA to change things. This patient received these fat cells in both eyes and became blind. So clearly, you're absolutely right that there's quite a lot of bad science attached to stem cells. So there's still much to do, but there are lots of progressions. And in the next 10 years, we'll see that in immunotherapy, particularly, the stem cells or cells which are, they call stem, but more adult stem cells, or certainly will be targeted. The stem cells in cancer exist also. So these cells are often resistant to all the therapies. And that's also another real obstacle for treatment of patients.
We have a question from one of our listeners who would like to know the relationship between traditional radiation, chemotherapy, and immunotherapy. When are these appropriate and when are they not?
So I'm not sure if Kelly wants to take this. We can do both. You will take it?
No, you go ahead, Michel. I think it's more in your wheelhouse.
So clearly, radiotherapy has been used in cancer for decades, probably over 60, 70 years. If you look at Marie Curie's work, after that, immediately it started to treat cancer with radiotherapy. But this is really the dumping a nuclear bomb on a patient. And since then, of course, radiotherapy has been really focused on target as much as we can. But still, for example, in prostate cancer, you will irradiate the entire bottom of your body to make sure that all the tumors are there. So this is still getting improving, and in fact, probably in 10 years from now, we're not going to do radiotherapy the same way. We'll be attaching radioisotope to particular peptide or antibody that will go, and they are called theranostic. So in 10 years from now, it will change a lot. The immunotherapy we're talking about, and we're talking into the video, is mainly the fact that we can try in many different ways to help the immune system kill the tumor, recognize it, chase it, and destroy the tumor cells. So that's also a much better approach in the sense that if it works, there's no side effect. And this is probably the most competitive field now in cancer and in oncology because there's so many of these new approaches that can be used.
As soon as you start talking about immune therapy, something that often comes to people's mind is what can they do to, quote, boost their immune system?
And ever since COVID appeared, of course, we've had all kinds of articles about what foods to eat and what sort of at-home remedies one can initiate to, quote, boost the immune system. So I'd like to ask both of you that. What do you make of this term, boost the immune system? Is this realistic? Is there something that people can do, foods that they can eat in order to boost their immunity? Maybe
there's a lot of artifact there too. I mean, one thing is good is what my mom used to say when I was young, and that's a long time ago. And Joe, I know you're an expert on that. It's really to have the best healthy food you can and keep your weight, be active, and that's by far the best way to keep your immune system working. As far as I know, there's no food that are really associated with the immune system, but maybe Kelly can contradict me.
No, I think, everyone wants that magic answer of, okay, I need to eat X number of apples per week to boost my immune system, and then I'm going to be safe. I think that gives people comfort. But in reality, there's no, it's very simple. It's a question of having a healthy diet, getting enough sleep, which is really important, and getting some exercise. And if you follow a fairly healthy lifestyle, keep your stress level down, those are all good things in terms of promoting healthy immunity. So, but unfortunately, there's no magic answer there that's beyond that, a healthy lifestyle.
And Joe, we can return the question to you. I mean, you have done a lot on this. You can say a few things too.
Well, I can't tell you how many emails I get every day asking about this supplement or that supplement. How much turmeric should I take to boost my immune system, etc. And you have to start out by telling them that the immune system is a very, very complex system. And there are many, many factors. I mean, cells and organs and the skin itself, and the body produces all kinds of antibodies. And there's no one thing that you can do to improve this. It's sort of like, asking, how do you build a car if all you're given is metal? It just doesn't work like that. There are many parts that have to be put together for immune system to function.
But if we go back to immunotherapy, though, just a point very quickly is that, in fact, all this complex system, we're trying now to analyze it and understand it better. And then each of these parts can be improved and one by one. So I think the immunotherapy is that, trying to see the best little button we can push to improve with drugs, with antibody, with other means. So that's that to answer the previous question.
Michelle, I mean, you've been in the cancer business for a very long time. What are the biggest changes that you have seen in your career in terms of the way that cancer is being treated?
Well, I'm not so old in that, but I can tell you that the big difference was the understanding signaling. And understanding how cells functions, how they, as you mentioned, many factors come in, and we explained a bit of that. Kelly did a great job on explaining at least the different lights open and on, and these are all controlled by genetics and proteins. So once we understand them, they are now excellent candidates of drugs or antibody, and they do targeted therapy. This has changed those patients which can have those therapeutics, targeted therapeutics, have immense amounts of improvement. On top of that, they are not so, the side effect are reduced. I'll let Kelly continue on this because I think it's something she knows also very well.
No, I think you said it perfectly, Michel. I think really there are two key advances, this idea of sort of personalized medicine and really understanding for each individual patient, what are the genetic drivers of disease, and really understanding that the signaling events, the factors within your cells that are dysregulated, as we described, and so that the physicians can then tailor your therapy for your type of cancer, for what is going wrong in your cells. I think that's been key. And then, of course, Michel and I would argue immunotherapy is a huge step forward in terms of truly understanding what's going on in terms of how low levels of inflammation can promote cancer, but at the same time, how we can re-engineer the immune system to fight cancer. And so really understanding immunology and how it contributes to cancer and can be used to treat cancer, I think is one of the huge step forwards in this field.
The Goodman Cancer Institute, of course, has trained many students, postdocs, etc. Some have gone into industry, and one of our viewers would like to know roughly how big has that impact been? What percentage of the people who have been trained there have gone into industry?
Well, I think I can give numbers. When you have a PhD at most university in Canada, it's about 18 to 20% of people that will be going into academia. The remainder of the people that got their degree will be probably 3/4 in industry, and the other quarter will be in the government agencies or regulatory like Health Canada. So really, there's at the Cancer Center, we probably in the past 20 years, 30 years, I've been there. You had about graduating 25 to 30 PhDs per year. But much more if you count master degree. So we're in hundreds of candidates, almost 1,000 PhD graduated since it opens. And so that's a lot of people. At least half of them will be in industry now and at different places. Like Kelly, I just saw an announcement of a new speaker at the Goodman Center who was my first student in 1992. And he's now head chief of a section at Merck in Boston. So it was really very nice to see that.
And I think
I know that one of the go ahead.
Sorry, Joe. I was just going to add. I think one important point to make is, and I don't think everyone realizes, is that people come out with a PhD or do their postdoctoral training at the Goodman Cancer Center, but they don't necessarily, many of them continue on as scientists and become lab heads and even CSOs at various small biotechs. There's also a slew of them that will then go into the business side or the marketing side. And so, the Cancer Center is not only training scientists, but also training sort of the other areas or other disciplines within pharma that are really important to bringing a drug to the market. So we can't understate the importance of that aspect of the training that goes on at the Cancer Center as well.
Well, I know that one of the most satisfying things about teaching and being a mentor to students is to watch them succeed and to hear back from them what sort of career they have been launched on. So, yeah, I find that very, very pleasing. Question about the lab animals and whether or not when research is done on mice, before that research is extrapolated to humans, is it tried on other animals that are more closely related to humans than mice?
So this would depend of the technology being developed. If it's mice are normally used, and it's important to note to everyone that the animal work we do at university in Canada, it's not only at the Goodman, are very much controlled by the Canadian Council for Animal Care. So we cannot do whatever we want the animals. We have people surveying to make sure that the animal are well treated and well taken care of. And the experiments are not abusing experiments. So it's very, very standardized and very controlled. So to finish the questions you had, so there are cases where drugs are developed in animals. At least we try to see if initially this will work. Mice are certainly 1,000 times less expensive than other animals for working if you start going the chain. But sometimes you need to go to larger mammals, pigs, and for example, on the stem cells for liver, people have now integrated this human stem cells into pockets that they put in pigs. And I think it's important to the size of the animals is important to understand if the technology will work. So they are still, but this is not generally done at the university. It's done by company. Universities, we don't have the money. It's rare that we have the money to do this type of work. And it's good because only the best thing of the university are taken by companies, and they're the ones which have to move it forward. And I think Kelly also will know that way very well.
This is a tough one. CRISPR, which is a technology, again, that's been in the news extensively. It's a technology for which a Nobel Prize was recently awarded. And the question is, what role will this particular technology play in cancer research?
So, Kelly, do you want to answer that, or?
No, I think you had a thought.
Yeah, okay, sorry. So just join in. So CRISPR so when I presented the video, people saw that we were able to manipulate animals, and the mutations we created in stem cells to make these animals were random. And we're trying to, by homologous recombination, try to do this, and 1 out of 1,000 cells got the mutations. CRISPR was a technology, was initially, in fact, coming from Laval University, and I don't think people have not given up enough credit to people at Laval University that developed this. But once you understand how can CRISPR work, CRISPR really use homologous recombination too, but it can target any genes we want. So that's, first of all, it was a mean to make mutations and follow what's the consequences, as I explained in the video really. But now people have 10 years of CRISPR, almost, and so they've used this all sorts of ways, not only to make mutation, but to repair mutations. And so CRISPR is used on all sorts of vector now. There's some disease of blindness that develop and caused by one single gene, and people have use CRISPR in animal first to show that they can repair and re-give the vision. And we see now many applications of CRISPR in all sorts of disease, to understand them, but to treat them also. So this will be, it's really a game changer in the biological science and biomedical sciences.
Okay, let me ask both of you this question. If you were able to project yourself into the future, let's say 100 years, how do you think cancer incidence and cancer treatment will have changed?
Good question.
Well, so I should let the young person answer that. Right? I'm not going to be there.
Who may actually be here 100 years from now if technology works the way that some suggest it will work.
Yeah.
No, I think it's hard to look forward to 100 years. I am an optimist, and I have real faith in terms of how quickly science is advancing, how drug development is improving in terms of its rate of success. So I don't see necessarily that cancer rates will drop, but I think that our understanding of cancer in 100 years will be more profound, and we will be better at developing therapeutics to treat it. And so I have real hope for the future that we're going to be in a good position to treat patients. I mean, that I'm an optimist. So Michel, I'll be interested to hear your.
So in my case, a few years ago, I had proposed a CFI grant, a big grant on modulating the immune system, and with family doctors, in fact. And I think this is going to happen very much. We will be using our own cells to be re-educated for the case of, for example, knee injury or muscle injury. You'll be able to restart your muscle stem cells and be able to treat yourself just by being diagnosed by a non-invasive technique. So I think it's all the cell therapy we're doing now, all the stem cell stuff, and the markers that trigger them. I think the toolbox of clinicians or the robots that will treat you will be immense, and will be able to do that very nicely. So there'll be a competition, in fact, Joe, I believe. It's not too much science fiction of changing stem cells versus, robotic arms or robotic ears. So we see this already. So would, for example, some treatment would be completely synthetic bioengineer, or there would be stem cells. We'll see. I mean, that would be an interesting directions that both of these fields will come up.
But I think you made an important point there, Michel, in terms of we'll have a larger toolbox. And I think that's what's key, is that we'll have multiple therapeutics and different approaches to treat cancer. And so back, a few decades, there weren't as many options. We didn't understand the differences between the different types of cancer, and so we couldn't tailor our therapies. We're moving really rapidly in that direction, and so having that toolbox of different approaches is going to make all the difference in the future.
Mm-hmm. Mm-hmm.
Someone has a very interesting question here about fruit flies, which are extensively used in genetic research. And the question is, can they be used in cancer research? Obviously, they're more readily available than mice.
Well, they've been used already. Many of the mutations that we find now in human cancer, these genes also exist in Drosophila, and when they're mutated, for example, wingless. It's called. It's a mutations that is found in Drosophila, and the way they found it is they irradiated a bunch of flies, and they start looking at those which are a bit weird looking. And then they identify those which had mutations and which genes they had mutations. And it turns out many of these mutations are also involved in development and our own cells working. So RAS, for example, KRAS is a different type of gene which is really common in certain type of cancer, pancreatic cancer, a very nasty cancer with this gene. And RAS was also found in Drosophila also. So yeah, they are used, but as far as model to test the medication, some people are using fish zebrafish to test drugs. But at the end, I think we're getting better and better at it, and probably these organoids from human that we can take and culture a bit of your cells. That would be probably the most important start. And then moving this to the clinic with microsampling or different techniques to be less invasive. I think this is where it's coming to us, reducing the animal use and improving different techniques that will resemble more the human being. And I think that's what's going to happen.
It's hard to make a fruit fly swallow a pill.
Exactly, but you can give a fruit fly a little drop of sweet stuff, and with the drug in it, it will do it very well.
Kelly?
I was just going to say, keep in mind, though, that the immune system has evolved greatly. There's even, huge differences between the immune system of the mouse and humans. And so Drosophila fish, they don't have the type of complex immune system that we have in humans. So that's really the limitation and why we can't do certain experiments in Drosophila. So they're very conducive to genetic research, but when you start thinking of the complex immune system in humans, it's just not recapitulated.
Well, some humans haven't evolved all that much.
Fair point.
Okay. Which brings us to an end here because we're running out of time. But we started with that elephant in the room, and I think we should finish with that as well. And Michelle, you were talking about mutations. And this is something that comes up all the time now among the vaccine hesitant people who believe that the vaccine can cause mutations by somehow insertion of genetic material into our DNA. And this, of course, is a scary business, and they are shying away from the vaccine because of such beliefs, which, of course, are not scientifically founded. So what do we do when people are led astray by misinformation about what mutations are and what can happen with the vaccine?
There's, of course, many different type of vaccine, but the most of the ones we had when we were kids and we're still giving to our kids are vaccine which have proteins, which have nothing to do with the genetics. They will just stimulate the immune response. The new vaccine, which are RNA based, and we have a fantastic person at the Goodman Center, Naum Sennenberg, that work on translation. So the only things here is that it's an RNA that is translated. I mean, it makes immediately a protein. It cannot revert to make a DNA molecule to integrate in our DNA. So this is also, you have, of course, you have to understand this little part of what molecular biology, but it's sure that this is not possible, and people have verified that. So I think they have to remember that these vaccines are tested have been tested, and then they've been used by millions, hundreds of millions of people now with very, very few bad side effects. So they have to be much more convinced that they're more chance to be affected by the disease than by the vaccine. And so I do encourage everyone. And my kid is my son is 11-year-old, and we both, him and I, looking forward for him to be vaccinated in the coming months. And then I hope that for that he'll be protected. He'll be protected for other people also, for the family members. So Joey, I think it's a good question, and I do hope people will look at the science behind this. Science we're not one bunch of people. We're all different people, questioning each other, validating each other. That's what science is all about. So at the end, what comes out of it is a very good consensus of safety, and that's what I would encourage people to do.
Kelly, you ever run into people who think that science has gone astray and that there's some sort of conspiracy between big pharma, big government, and big academia to hide effective treatments from people?
Yes, I mean, this is a running theme, I think, that I face meeting different people with different viewpoints. And I always find it hard to understand because, I trained and grew up among scientists, and as Michel alluded to, we're a tough bunch in terms of we really hold each other to account, and there's a constant debate back and forth over the quality of the data. And I've yet to meet a scientist who was rushing with and not following the data. And so, I think all we can do is try and promote science, try and educate the public about science and how science is investigated, how it's generated, how we scientists think. And I think that's the best way is education, Joe, to be honest.
Well, both of you have done a magnificent job in doing exactly that, in promoting science and explaining what you do to the public. And I think they have been not only informed, but I think they've also been entertained tonight because of the wide-ranging discussion. So I thank you both very much, and also the Goodman Cancer Institute for all the work that is done there, which is increasingly recognized. And Dr. Tremblay has just received the Prix de Québec, which is Quebec's highest honor. And Dr. Morag Park, the director of the Institute, also has received that prize. And obviously, it is extremely well deserved. And thank you, viewers, for sharing this evening. And of course, there will be other public lectures organized by the Goodman Cancer Institute dealing with various aspects of cancer. I know that it is a terrible disease. Nobody wants to hear this word, but it's also encouraging to see how much research is being done, and that we keep getting closer and closer to that finish line. So thank you very much, and thank all of you for listening, and we will see you next time.
Thank you. Good night.
Thank you.
Good evening.
Thank you for joining us. It was an honor to sponsor tonight's event, and we encourage you to come back again for the second lecture later this spring.